Welcome to an Atlas video tutorial on modules. This is a feature of the RealX software, which has better handling of irreducible and standard modules and also virtual modules in the basis of irreducibles and standards. I'm going to assume some familiarity with the software, in particular that you have the software installed on your system and you have it running. So let's begin by firing up RealX, which I do from the command line thus. And I get a little bit of information about which version I'm using. And the first thing I always do is I want to load in a bunch of auxiliary files with some definitions. I've combined all of these into a single file called my. So this less than says read in the file my.rx. And that's what it just did that, and it told me along the way all of these things it was defining. And it read in a bunch of other files. For example, it tells me that it read in the file kl.rx, that's the Kazhdan-Lustig polynomial file. And a little further down here it says it read in the file the Hermitian, about Hermitian, computing Hermitian forms, and unitary, and now it's done. It's finished reading this file. Now there's one other file that I want to focus on, and so I'll load that in separately. That's called Coherent. And this is the file with a bunch of definitions about coherent continuation and such. So let's begin with a very simple example. Let's look at SL2R. And let's take T to be trivial of G, and this is a parameter. So it just says here value is a parameter. And let's print the block of this parameter. This has three representations in it here, labeled 0, 1, and 2. And the first two of them are discrete series, and the third one is a principal series. This is the principal block at infinitesimal character rho of SL2R. And so far, I hope this is very familiar to everybody. This is the first example of parameters in Atlas. Okay, now the main point I want to illustrate here is that up until now, Atlas has worked exclusively with these parameters, and it interpreted a parameter as being a parameter for an irreducible representation or for a standard representation, depending on the context, and it didn't make it particularly clear which it was. You had to figure it out from the context. So let me illustrate that with a couple of examples. I can ask for the composition series of a parameter. And the composition series is the composition series of a standard module. So implicitly it's interpreting this parameter as the parameter of a standard module. And it's returning this list of parameters, which is, because of the context you know, is a list of irreducible modules, each occurring with multiplicity 1 in the standard module. Each line in the output is giving multiplicity 1 times an irreducible representation of the given parameter. Okay, now another thing I can do is ask for the character formula of a representation. Now the character formula is something you ask about an irreducible representation. So when I ask character formula of T, it's going to interpret T as an irreducible representation and return this. Notice this. What this means is this is a virtual linear combination of standard modules. Notice that the coefficients at the beginning are plus and minus 1s. It's saying that the trivial representation can be written in the Grothendieck group as a principal series minus 2 discrete series. Okay, I suggest if this isn't familiar to you, you pause the video here and you think about this example. Because we are going to write it in a different way next. So what's new about the modules version of RealX is that you now have something called j of a parameter. So I'm going to set j equal to j of this parameter t. And what this is it's the original parameter. That's the parameter t, together with just a little flag here, a string that says IRR, meaning think of it as an irreducible. And there are also standard modules denoted I of a parameter. So if we look at I, again, it's exactly the same parameter, but now the letters STD indicate that it's to be viewed as a standard module. And I'm going to be dealing a lot with these I's and J's. So for example, I now look at the composition series of this module I, and it says it's the same answer as before, this linear combination of parameters, with the additional information of them being irreducibles. And there's a function called mprint, or module print, which makes that clear. If you do module print of this, it says what I'm getting out is 1 times the irreducible module j of 0, and then those 3 irreducible modules labeled j. I need to interject here. I've discovered that when I made this video, there was a bug in the mprint command, and all of the lambda values are off by row. So every time you see the output of mprint, you should imagine adding row to the second argument lambda. Sorry about that. I will fix that in a revision of this video. Okay, so the opposite example is I can do mprint of the character formula of the irreducible, and now it says that what you get is a linear combination with some plus or minus ones of standard modules, which are indicated by I. So the extra information of whether we're looking at irreducible or standard modules is now indicated in the output by the I and J. On the other hand, the software also looks at the input side. Suppose I asked for the composition series of J. Well, that's probably not what you meant, because J is irreducible and you only ask for composition series of standard modules. So the software will return an error if you ask for that. Okay, so we'll look at some more examples now. To do that, I'm going to look at the entire block of the trivial representation. So let's set B to be the trivial block of SL2, which is to say G. And let's look at this block for a moment. It's just a list of parameters, 3 of them. And it's 2 discrete series and a principal series. And I just want to give names to these things. So I'm going to say P0 is the first parameter, and P1 is the second parameter, and P2 is the third parameter. These are just parameters. And there are also the corresponding irreducible representations. I'll call those J0 is J of parameter 0. And similarly, J1 and J2. And I'll also define the corresponding standard modules, I0, I1, and I2. So you should always think of these 3 sets: parameters, irreducibles, and standards, all of which are in bijection. And so here's J0, for example. This is a discrete series representation. And let's look at the composition series of the principal series. I looked at this before. It says that it's the sum of these 3 irreducibles. And the software knows how to compute with virtual modules. So in particular, you can say J0 plus J1 plus J2. That's a virtual module given as a sum of irreducibles. And you can ask if that's equal to I2. And now this is an equality in the Grothendieck group, because on the left side I have a sum. That means implicitly I'm working in the Grothendieck group, and it converts the right side to be an object in the Grothendieck group and confirms that these are equal. This brings up an important point, which is that the software does a number of type conversions. For example, in this case, it knows to convert the standard module I2 to an element of the Grothendieck group. The software tries to be very smart about this, but on occasion these type conversions can be a little bit tricky. So some care is needed when doing type conversions yourself, or in situations where the software might be doing type conversions for you. Okay, let's do a couple of other examples with these virtual modules. So let's start again by looking at the composition series of the principal series. It's the sum of these three irreducibles. And the composition series and character formula functions can be applied to virtual modules. So, for example, if you look at the character formula of the composition series of I2, of course, these two operations are inverses to each other, and what you get is exactly the original module I2. Let's just check that's really what happened. Indeed. And similarly, in the other direction, the composition series of the character formula of something gives you back the irreducible you started with. So let's just maybe do an illustration about using loops to look at examples. Let's take G to be SP4, and let's run over the block of the trivial representation. The P is running over the parameters in the trivial block. And for each one of them, let's check, is it true that the let's see, we're going to check that the composition series of the character formula. Now let's see, character formula is something you apply to an irreducible. So character formula of J of P, that had better be equal to J of P. And we're going to check this for all representations in the block of the trivial representation of SP4. Let's do another kind of loop. Let's run over the same block, and for each element of the block, let's print the parameter and also the composition series of the corresponding standard module. This is the kind of information you might want to see in one place. So here, for example, let's scroll back up and take a look what we got. The very first line says final parameter x is equal to 0, and it's equal to j of something. That is to say, that's a discrete series, which is irreducible. The first four parameters are discrete series. Their composition series are length 1. And then there's a module here with a composition series of length 3. And then all the way down here, the second from the last is the trivial representation with the longest composition series. Now I want to look at another new feature of the software, which is the translation principle. I'm going to start just by looking on the level of parameters. So let's start with the discrete series parameter for SL2. Its infinitesimal character is rho. And the translation parameters, translation functors on the level of parameters enable you to translate this parameter to another infinitesimal character. So for example, I can translate it to infinitesimal character 2. I get a new parameter, and here it is, and its infinitesimal character is 2. In terms of representations, I've translated the discrete series from rho to 2 rho. Now, translation is only defined for characters of the Cartan, which in our parameterization are integers, so I cannot translate to infinitesimal character 3/2. I will be informed that that is an error. Now, another thing I can do is I can translate to infinitesimal character 0. That's perfectly fine. This is the parameter of a limit of discrete series. So let's call it P00. And let's translate parameter 1 also to 0. So these are two parameters for the two limits of discrete series at infinitesimal character 0. Let's also look at the translation to 0 of the parameter P2. This is the parameter of the trivial representation, which is to say the standard module is the reducible principal series. And if I translate this parameter to 0, something interesting happens. I get a non-final parameter. So this is a perfectly good parameter, but there's something less than perfect about it. Let's look and see what happens. Let's give this thing a name. Let's call this P20. And let's take its standard module. That's a perfectly good thing to do. And it's just the same thing considered as a standard module. But there is no unique irreducible quotient. And if I try and take one, it will complain because the parameter is not final. So this is the thing which is the direct sum of the two limits of discrete series. So let's look a little bit more closely at what's going on here at infinitesimal character 0, and at the same time I'm going to introduce translation of irreducible and standard modules. So let's look at the translation to 0 of not the parameter 0, but the irreducible representation J0. This is an irreducible representation. It's the limit of discrete series at 0. And let's check. If you translate this representation to 0, what you're getting is the irreducible representation of the translation of the parameter. So let's just see that that's really true. Indeed. And so let's set J00 to be this representation. This is a limit of discrete series. And let's also look at J10, which is the other limit of discrete series. That's the translation, excuse me, I'll define that as J of P10. Okay, so now I'm going to check an identity in the Grothendieck group. Let's look at J00 plus J10. The sum of these two limits of discrete series is in fact equal to the standard module defined by this parameter, this principal series parameter at infinitesimal character 0. The sum of two limits of discrete series is equal to an induced representation. Next, I want to illustrate how to use translation of parameters to define representations conveniently. And I'm going to use this to define the irreducible principal series at rho. And a nice way to do that is the following. We start by setting Q to be the spherical principal series of my group G at infinitesimal character 0. So the spherical principal series is a function which is predefined. So this is a parameter. So I'll check its infinitesimal character, of course, is 0. And let's set I to be the corresponding standard module. And let's check that, in fact, I is indeed irreducible. The composition series of I has just one term. So this is the irreducible spherical principal series at 0. And now I simply translate the parameter to rho to get the irreducible principal series at rho. So I set Q rho to be the translation of this parameter to rho, which is to say 1. Oops, sorry, that was a misprint. I forgot to say translate 2. And so let's look at what Q is. It's a parameter that looks like this. Its infinitesimal character is 1. And let's look at its composition series. If you take the composition series of the corresponding standard module, you see that it is irreducible. It's not spherical, but it is irreducible. Okay, just for fun, let's look at a bigger example. Let's do something similar for the split group E7. So let's set Q to be the spherical principal series of the split form of E7 at infinitesimal character 0. That's a representation I understand reasonably well. There it is. There's the parameter. Here's a new command which I had mentioned before, full status codes, tells you what all of the roots are. They're all of type Rn, which tells you that this is in fact irreducible. And another way to check that is to compute its composition series. And let's do that. And it takes almost no time, even though it has to compute some Cauchy-Listic polynomials. And of course, the infinitesimal character is 0. And now let's translate this to rho to get the irreducible principal series at rho. Let's set irreducible principal series at rho to be the translate 2 of this parameter. Whoops. Let's set the q rho to be the translate of this parameter to a rho. And there it is. And let's look at the status of the roots of this new parameter. And of course, they're the same. That's what the translation principle does for you. And let's look at its composition series. This is now going on at rho, the composition series of the corresponding standard module. And indeed, it's irreducible. I'm going to explain a bit more about translation of parameters and modules now. The translation of parameters is intended primarily as a convenience for the user, as a way of taking a parameter at a given infinitesimal character and getting a new, essentially the same parameter at a different infinitesimal character. And as long as one's working inside a given Weil chamber, the standard modules and irreducibles behave in essentially the same way. On the other hand, the translation principle does allow one to translate modules from the dominant chamber into other chambers, and that's a substantially more subtle notion, and that's the topic of coherent continuation, which comes up a little bit later. But for now, I want to explain these issues a little more carefully, the issue being translation of parameters versus translation of modules. So let's start with back to our SL2 example. So remember, P0 is this parameter for the large discrete series, and I can translate it to 0, and I get a perfectly good parameter at infinitesimal character 0. And I can even translate it to -1. Now, -1 is not dominant, so this is not a standard parameter, but formally speaking, it's perfectly well defined. It's called a non-standard parameter. Atlas doesn't really do anything with these parameters at the moment, but formally speaking, they're perfectly well defined, and at some point the software may make some use of them. Now, on the other hand, in the setting of representations, you can translate the irreducible discrete series at rho to infinitesimal character 0 with no problem, but if you try and translate it to infinitesimal character -1, it complains the target infinitesimal character is not dominant. So the modules themselves cannot be translated outside of the dominant chamber. Let's look at a few more examples for SL2, which illustrate some other subtleties about the translation operation. Let's look at the parameter P2 for the standard module at rho. Of course, I can translate that to 0. I've done this already, and I get a perfectly good, albeit non-final parameter at 0. And I can even translate it to -1, and rather interestingly, at -1, I get a perfectly good final parameter. That's a topic for another day. In any event, it's a perfectly good parameter. Let's look at the translation of an irreducible representation, the trivial representation, which is labeled J2. If I try and translate J2 to 0, it vanishes. It's 0, and so I get an error because it's not actually a representation. Translation of an irreducible representation is supposed to give me a representation. If I wanted to do it in the level of virtual modules, I can do that, that would be well defined. So if you insist on that, we could do it this way. If you translate the virtual module of J2 to 0, what you get is the empty virtual module. Okay, let's look a little more closely at some of these objects that we have now. So let's start by, let's take capital P to be this virtual representation. I use capital P to remind me that it's a virtual module, which is called a parampole. And it's a virtual module as a sum of irreducibles. And let's take Q to be the translation to 0 of the first discrete series parameter. And that's the limit of discrete, that's the parameter at 0. And let's translate this parameter back from 0 to 1. And that's perfectly fine. I can translate parameters away from walls, and I get the discrete series parameter again at rho. Again, translation of parameters is a formal construction. On the other hand, if I try and let me check that what I get is, again, the discrete series parameter at rho. On the other hand, if I try and translate this irreducible, I get this error message: you cannot translate modules to less singular infinitesimal character. So the point is that translation of parameters across walls or away from walls is formally a very simple operation, but translating representations away from a wall is not, and that uses the phi function, which I will describe next. So that brings us to the phi and psi functors for translating to and away from walls, which go back to the original paper by Zuckerman on the subject. So let's start by taking ds0 and define it to be psi of j0, 0. And what that means is the psi functor takes the irreducible representation j0 and translates it to the 0 root wall. And in this case, that is to say it's translating to infinitesimal character 0, and this is exactly the translation we talked about earlier. And let's check. This is an irreducible representation at infinitesimal character 0. So that is to say, translation to root walls given by simple roots are given by this psi functor. Okay, so let's do a little more with this. Let's take ds1 to be the psi functor applied to the other discrete series. So that's the other limit of discrete series at 0. And let's look at what happens if we translate the standard module I2 to the 0 root wall. Well, we've seen this example before. I'm doing it again in using the psi functors. Notice that ds0 plus ds1 is equal to I in the Grothendieck group. The sum of the limits of the two discrete series is equal to the reducible principal series at 0, and that's obtained by translation from what's going on at infinitesimal character rho. Okay, next, the more subtle phi functors come up. These are the functors for translating away from a simple root wall. And they typically do not take irreducibles to irreducibles. And so the result is necessarily landing in virtual modules. So let's see how that works. For example, let's compute phi of this limit of discrete series ds0, translating it away from the 0 root wall. And this third argument is, well, I need to tell it where I want to go to. I'm going away from the zero root wall, but I still have to say what infinitesimal character I want to land at. So let's say I land at infinitesimal character 1. And if I compute this, I get a virtual module. Let's see, it's 2 irreducible discrete series plus the trivial representation. And that is to say, if you take the limit of discrete series and apply this phi functor to it, you get 2 times the limit of discrete series plus the trivial representation. And as I said before, you need to specify the target infinitesimal character as the last parameter. I'd like to illustrate another aspect of these functions using the same example. Let's set limits of discrete series irreducible to be psi of j0, 0. So that means that you take the irreducible and translate it to 0. That's what we've talked about quite a bit. And let's let LDS STD be the translation of the corresponding standard module to 0. And of course, it's the same representation, although if you ask if they're equal, the software will complain because one is standard and one is irreducible. But if you want to check it, you check that the corresponding statement is true about the virtual representations, and the answer is true. Okay, so far so good. We've already basically seen this. Now I want to look at what happens when you translate these things away from the wall. So let's set A to be the translation away from the wall phi of the irreducible limit of discrete series away from wall 0 with target infinitesimal character 1. And let's see what that is. First, let's set B to be the corresponding thing except applied to the standard. This thing viewed as a standard module. So let's look at these things. A is this sum of 2 irreducible representations, and B is this linear combination of 3 standard modules. In fact, A is equal to B. The point is that the software writes things, if you start with a standard module, it writes the result as a linear combination of standard modules. And if you start with an irreducible, similarly irreducibles, you're getting the same answer as confirmed by this test. All right, now we can do both of these. We can combine these two steps in this single function called phi psi. And what this does is it takes your representation at regular infinitesimal character, pushes it via psi to a single root wall, and then phi back out. And you don't need to specify the target infinitesimal character now because you're going back to the original one. And so the only argument that you need is the root wall. And you see that if you take the discrete series and translate it to the wall and come back out again, you get 2 times the discrete series plus the trivial representation. That brings us finally to the subject of coherent continuation. This is an action of the Weil group on the space of virtual characters with a fixed regular infinitesimal character, actually the integral Weil group. And it's defined in terms of the coherent families, which we discussed earlier, and it's also closely related to the translation functors we've been talking about. So let's start by looking at a simple example. Let's take, as always, the holomorphic discrete series of SL2 at infinitesimal character rho for starters. This is pi, the irreducible representation described here. And let's apply a simple reflection to it. So it's an action of the Weil group. The base case is an action of a simple reflection. So in this case, I'd like to compute the action of the simple reflection on the irreducible representation pi, which of course is being interpreted as a virtual character. The result is going to be a virtual character, so it's best to use the mprint command to have a nicer looking output. So let's look at mprint of this. And the answer is a sum of two irreducible representations, the original discrete series plus the trivial representation. And I'm just showing you that that's the same as thinking of pi as being a virtual representation. That's what it's implicitly doing. So this says that the coherent continuation of the discrete series is the discrete series plus the trivial. And where this comes from is the coherent family. So you take the coherent family of pi and you evaluate it at S alpha applied to rho, which is to say -1. So let's check if the coherent action, the coherent continuation action of 0 on pi is equal to the coherent family evaluated at -1. And that's true. Now, it turns out that there's a relationship with the translation functors as follows. You start with this representation pi and apply this operation phi psi to it. And let's see what you get. You get 2 times the discrete series plus the trivial representation. And that's pretty close to what I got by the coherent continuation action. And in fact, you see that there's an identity in this case, which is that the coherent continuation action of a simple root plus pi is equal to this functor phi psi. And that's an important general identity in the theory. Let's see, that's true. And that holds in general for any virtual module. Let's look at another example. Let's look at the coherent continuation action of the simple root on the trivial representation. Well, we get minus the trivial representation. That we knew because if we take the coherent family of the trivial representation and evaluate it at S alpha applied to rho, which is to say -1, if I get my parentheses in the right place, we'll see what we get. This coherent family is equal to minus the trivial representation. I'd like to conclude with a slightly bigger example. So let's take G to be SP4R. This is the rank 2 group. Rho is 2, 1. And let's start with our favorite representation, one of the large discrete series at infinitesimal character rho. I'll call that pi. That's an irreducible representation. And let's make the coherent family defined by pi. So let's just make sure that the coherent family evaluated at rho is indeed equal to pi. And it is. And let's evaluate this coherent family at the point 2 minus 1. Now this is going to be a virtual module, so it's good to use the mprint command, and I see that it's the sum of these two representations, the discrete series plus another irreducible. And according to what I just said, this should be the same thing as the coherent continuation through root 1, which is the second root, the long root applied to pi, and indeed it is. Okay, so this is the Weil group after all. Now that I'm in type C2, I have two different roots, so I can apply one and then the other. So let's apply coherent continuation first by root 1, which I just did, and then apply root 0, apply that to pi. So that would be done in 2 steps like this. And if you look at what you get a sum of these 5 terms. And of course, the software enables you to do this in 1 step. The Weil group element is written this way, 0, 1. You apply that Weil group element to pi, and indeed, that's what you get. Okay, so this coherent continuation action is the same as evaluating the coherent family at what point? Well, so let's see. The Weil group action, we first applied S1 to take 2, 1 to 2 minus 1. And then we applied S0, which switches the two factors, which takes us to minus 1, 2. So that says that this thing that I just computed, the coherent continuation action through these two roots, that should be equal to the coherent family evaluated at the point minus 1, 2. Well, of course that's true. I'll conclude now with a couple of other calculations with the same example. I'd like to take I to be the standard module of the same parameter. That is to say, I and pi are the same virtual module, viewed either as an irreducible or a standard, in both cases, the discrete series. And let W be the long element of the Weyl group. And I'd like to apply this element to the representation. So let's let P be the action of W on pi. And let's let Q be the action of W on I. And let's look at what P is. This is going to be some linear combination of irreducible representations, and there it is. On the other hand, Q is a linear combination of standard modules. Now, these look rather different, of course, but they are indeed equal. Let's check P is equal to Q. The answer is true. And to illustrate some of our commands from earlier, if you take the character formula of P, you get exactly this linear combination of standard modules in Q. And conversely, if you take the composition series of this virtual module Q, you get exactly the irreducibles, which are found in P. And for one final check of the software, let's check and make sure that one of the identities in the Weyl group holds. The long element of the Weyl group has order 2. So this element of the Weyl group is the identity. If I apply it to pi, I sure had better get pi. And on that true value, I will, as they say, quit while I'm ahead. Thank you for your attention.